Welcome to presenting continuous distributions. So the idea is we want a sort of graphical representation of continuous distributions. So we want a graphical representation of a continuous distribution. And ultimately, we want one that shows the probability. So we had the table of probabilities for discrete distributions. So we want a graphical representation of a continuous distribution, which can be used for finding probabilities. So there's a general basis behind this is just we'll look at histograms. So if we say we're looking at, there's one in here reading on foot length. So for example, if we looked at, we can do the same with height. Let's go with in inches. If we were looking at height, we could have a histogram that maybe starts at 55 inches, 60, 65, 70, 75. And we could do a very broad histogram where we go counting by fives. And we have our histogram bar for 55 to 60. And then 60 to 65, 65 to 70, 70 to 75, etc. Right? And in this one, we have a sense of how many fall in these wide ranges, but we could get more precise. So then from here, we can go more precise. And now let's say we count by twos. So maybe we have 56 to 58, 58 to 60, 60 to 62, 62 to 64, etc. This is nowhere near precise by any means. This is just sort of showing we could go more precise, narrow our categories. So instead of counting how many people fall between 60 and 65 inches, we just count from 60 to 62 inches and then 62 to 64 inches, etc. We could go even more precise from here. So this is essentially by grouped in 2 inches. So this is grouped by 2 inches. This one was grouped by 5. Inches. We could do by ones and have even narrower bars. So this is by 1 inch. And we could just keep going narrower and narrower and narrower and narrower. And as we go, this graph starts to take on more or less the same shape. So if we look behind all of these, if we sort of outline the general shape, these all are taking essentially the same shape. And notice that in this last histogram, the the boxy shape of the histogram almost precisely fits the curve behind it. So in this case, the histogram outline very closely fits the curve drawn. And if we continue to let our histogram bars get narrower and narrower and narrower, eventually the histogram and the curve will have essentially exactly the same shape. So if we continue to let the histogram bars get narrower and narrower, eventually the histogram outline will essentially be the curve. So what we do instead then is, instead of looking at the histogram, we just look at the curve behind it. So instead of looking at a histogram, we use the curve behind. By some rescaling of our y-axis, we can make it so the area under the curve is equal to 1. So by some rescaling of the y-axis, we can make it so that the area under the curve is equal to 1. And then this becomes what is called the density curve. So this rescaled curve is a density curve. So we have our curve. And if we were to, say, calculate the space filled in here, that area equals 1. And that means since total probability is 1, we can now actually use this curve to find probability. So we can use this to find probability by using the area under the curve. So we can use this density curve to find probability. So if we want to find the probability of being between two specific values, so let's say we want to find the probability of landing between here and here. So the probability of landing in this region is equal to the area between those values under the curve. We will play around with this a lot more as we go forward. We will be focusing on very specific density curves because technically the area under a curve is a second semester calculus concept. So we will have technology and charts to do the calculations for us, but those will focus just on what are called normal curves. So for now, just keep in mind that this curve essentially comes from the histogram. That's the outlining shape of the histogram. All right, so that is a density curve.